So for those of you guys that are worrying about that, I'll get that in there so it's ready to go by Wednesday. This doesn't look real easy to read over there, even though I've got nice dark. There we go. Our final in here is going to be Monday at 8:30. So we're going to have Monday at 8:30 is when the final is going to be over here in Tonkawa, or over here in Enid and in Tonkawa for this class. So we'll get this one. First one up is this one. And remember, it's only going to be over optics. So, and I think I've got everything. We'll look at it here in just a second. So let's look at what I've got. Let's go to WebAssign. And we're going to do present. Let's see, that's the wrong class. This is this class. Everything is out there. This one should be available. That quiz, that's the quiz on ENM waves, reflection, and mirrors. And that'll help you study for the final, because the final is only going to be over optics. So everything is out there. All the homework's out there. Everything's out there for you guys if you wanted to start working ahead. So it's all there. And the test will get posted in Blackboard, not in WebAssign. And that way, if you want to show your work, you can turn in your work or upload your work, and it'll be in Blackboard. It won't be a PDF file. It'll be multiple choice. So you pick A, B, C, or D. But if you want partial credit for showing your work, then you just turn in your work. Okay. So that gets us that. So I'm going to try and go back and forth between these diagrams, because that make it a little easier to see. But right now I'm going to go to the document camera.
When did you say that test will be due?
Wednesday.
Okay.
Wednesday. So where we were on Wednesday was we had just done, or I had just kind of covered Snell's law. So let's do a couple of drawings, a couple of pictures to see what's going on. So I've got a ray of light travels from air into a fused quartz plate. And fused quartz, if you go and look, so I got a ray of light travels from air into a fused quartz plate, and if you go look at the table, and if you're in WebAssign, you'll click on where you want to, you'll click on that other piece to find out where things are, and it'll tell you that for fused quartz, the index of refraction is 1.458, and we're going to have the light hit the plate at an angle of 43 degrees from the normal. And we want to know what is the refracted angle. So basically what we've got happening is this. I've got my my angle coming, or my light coming in. It's going to hit, and I'm going to use red just like a helium and neon laser pointer. And this is air, and air's got an index of refraction of 1. And we know that since this is greater, this is 1.458, that we know this, so this is going to be my angle of incidence, and we're going to come in at an angle of refraction want to calculate what that angle of refraction is. So it's going to be my N1 sine of the angle that comes in is going to equal N2 sine of the angle that's reflected or refracted. So I get N1 over N2 sine of the angle is going to equal the sine of the new angle. Plug in the numbers, I get 1.485 sine of 43 degrees. And that's going to equal 0.468. So my refracted angle is going to be the arc sine of my 0.468. And that gives me 27.9 degrees. So don't make these harder than they are. Now, I think one of your homework problems goes the next step, gives you another index of refraction. So you have to kind of figure out what your angles are when you hit this part. Well, if that's a right angle, we know that this angle is the complementary angle, so that's going to be 90 degrees minus my angle of refraction. Or if I do the old adage of I've got parallel lines, we know that this is also going to be my angle of refraction. And then we can just step through the different layers. So they aren't hard, they're just stepping through each individual layer. So that's the refraction one. Let's talk about a device. This is because optics was all about devices, and that's why I like devices. So if I look at a periscope, okay, so here's my periscope, and depending on exactly how I'm dealing with my periscope, and it's like this, and my periscope is essentially got a mirror on this side and a mirror on this side. Now, some periscopes will actually be mirrored in here to catch other things, to give you more other things, but if you look at it from the perspective of what the periscope is really doing, so here's my eyeball, right? So we can put eyelashes on it just so that we know that's my eyeball. And I've got a ray of light that comes in. So I've got my ray of light that comes in, and then it's going to refract off, and it's going to come back straight down through my periscope, and we can actually go ahead and do the law of reflection, that this angle and this angle, so that the angle has got to equal the angle prime, and if I use a protractor, I can go through and use that protractor and do it. But what happens is it's going to come in and it's going to bounce off this mirror doing the exact same thing, and the ray is going to end up in where my sight line for my eye. So periscopes, cool toys, so that you can actually get pieces. Then let's think about some other things that are happening. And so a lot of this, when you guys do your homework, it's all about keeping the angles straight. So if this is 60 degrees, so if I've got a mirror here, a flat mirror here, and I'm going to have my ray come in, okay? I'm going to have my ray come in nice and straight here, and I've got my normal. You can play with the geometry to figure out that this is going to be 30 degrees. So there's my other ray that's going to bounce. Well, if that's 30 degrees, then this has got to be 60 degrees, which means that this is 60 degrees, and that means that that's got to be 30 degrees, and I can project right how my beam is going to bounce out. So for most of this, it's just playing with geometry and how the angles are bouncing, which is why I love ray optics. Ray optics is you can use you can use your protractor and get the answer just by playing with the ray optics. And I'll show you something here in just a second on the internet that you can play with as well. But I want to do another problem because you're likely to see this problem again. Hint, All right, so I've got a flat mirror and a flat mirror, and we're going to separate this by a distance, and this is not drawn to scale, but you may want to draw these to scale, okay? Because if you draw them to scale, and you are allowed to bring a protractor to the test, okay? You're allowed to bring a protractor to the test. So if I have that, and then I'm going to say that this side, this length here is 0.5. This is 0.4 meters, 0.5 meters. And I'm going to have a ray come in. So let's use red just so that we can keep track here. And I'm going to have this ray come in just such that it's just coming in right at the edge of our little device. Okay? And like I said, this isn't drawn to scale. But we're going to say that this is equal to 30 degrees. Which means that this has got to be 30 degrees. And we're going to get another bounce, because it's going to come in and it's going to bounce. And if these are parallel, that's got to be 30 degrees. And this has got to be 30 degrees. And we got another bounce. And we can do that all the way across. But again, I said this isn't to scale, okay? This isn't to scale. But we want to know the number of times the beam hits before it exits. Okay, we want to know the number of times the beam hits before it exits. So this just becomes a geometry problem. I know this side, I know the angle. I'm going to need to know this side, okay? So y over d is going to equal the tangent of the angle. This is going to be y. So y is going to equal d tangent of the angle. And this time we know that d is 0.4. My angle happens to be 30 degrees. And so this ends up being 0.23 meters. So that's 0.23 meters, which means this is going to be 0.23 meters. So if I do two of those, I end up with 0.46 meters. So when this bounces over here, if this is only 0.5, right? And if I add another 0.23, or let's go ahead and do it 0.5 minus 0.46, means I'm going to be at 0.04. That means this one is going to bounce out and not hit another wall. And so it's going to hit 2 times before it bounces out. Remember, this isn't drawn to scale. And you're likely to see a problem like this. Kaleidoscopes, that's what the whole idea behind a kaleidoscope is that I've got a flat mirror. I have a flat mirror. Depending on how intricate your kaleidoscope is what we end up with, and that's why you're going to get those different pieces. Mirrors are great for optical illusions, right? Mirrors are totally great for optical illusions, so you can play with the optical illusions. Let's do one other kind of problem associated with refraction. We talked about this on Wednesday. This day is Friday, so that was Wednesday. So I have the surface of the water. Water has an index of refraction of 1.333. Air has an index of refraction of 1. And what we want to know is the critical angle where I'm not going to have light leave the surface. So basically what we want to know is, I'm going to go ahead and put in my normal. We want to know the angle that results in something like this. That's what we want to know. And if you go in and you look in your chapter and look at the derivation, my sine of my critical angle is going to be N2 divided by N1. And in this case, this is N2, this is N1. So you think about where my ray is and where my ray is going. So the critical angle is going to be the arc sine of N2 divided by N1, and that ends up being the arc sine of 1 divided by 1.333, and that's going to give you the angle being 48.6 degrees. Okay, now I'm going to go down here for a second. Okay, I want to go here. All right. So hopefully you see my Google page. In Google or in Chrome, oh, it says I'm not signed into Chrome. There is a, well, we can go there. Let's go to Chrome apps. No, that's not it. Okay, I'm going to come out and sign back in. No, I should have come in. Just didn't sign in. I don't want themes. There is an extension that allows you to play on Chrome, and it's called Chrome Optics, and it's just not coming right off the top. But you can actually play with doing various optical things, and then I'll go ahead and get you a link to it. But there's also another simulation out there to play with for optical simulations. And if we go to physics, I think it's ray optics or something on the Chrome. The Chrome one is really, really nice because you can change the index of refraction to whatever you want it to be. But this one is here as well. This one gets you your geometric optics, but it's got to have Adobe Flash Player, which none of our computers have anymore. But I'll put a link to where it is out there so you guys can play with it, because it's a lot of fun to play with, and you can create a mirror that's got various rays. You can play with bouncing, and so it allows you to look for a variety of different things. So let's kind of look at it. So let's start talking about, I'm going to go ahead and do a presentation. So when we're dealing with mirrors, so now we're jumping into the next chapter, okay? This is the next chapter, and I think it's chapter 23, and we're dealing with mirrors, and so we want to look at some conventions. Basically what's going to happen to us, this is going to be called the real side of the mirror, and this is going to be called the virtual side of the mirror. Virtual means that we're going to perceive that it's there. But if I were to take a piece of paper and put my piece of paper right here behind the mirror, nothing's going to show up on it, okay? Light doesn't actually make it there. So that's why it's called virtual, okay? Even though our eye is going to perceive that something is there, if I were to put a piece of paper right here, I wouldn't see anything. Now, if I have a straight piece of glass, the rays would actually make it to the paper, and I would actually be able to get the image on paper. So a real image is going to be an image that the light actually makes it to, actually just like shining it on a piece of paper or a screen. We're going to use the convention that O is my object, so this is what I'm physically looking at. A lot of books will use a little candle, a lot of books will use, we're going to actually ultimately use an arrow to represent our objects. And then I is going to be our image. So this is going to be the image. We're going to use the convention that the distance between the object and our surface is P, and the distance between that surface and our image is Q. And what happens to us is, using the law of reflection, the actual ray is going to hit the mirror. There's my normal, and I can use my reflection, and it's going to come towards my eye. But I'm going to take this ray and extend it to the back to where the image might be there. So that's why we call it geometric optics, because if I use my protractor, I can actually draw the line where it's going to be. And I can do that for each ray that's coming off, and it's going to give me a place where the mirror is going to occur. So if I think of putting my hand in front of the mirror, which is why things look reversed in the mirror, is because the rays are going directly from my thumb to the spot behind the mirror where my thumb would be, and then back. I'm not flipping it to make it oriented exactly the way I would see it. So if you're looking at yourself in the mirror, you can start playing with, well, where are those rays going and where are they coming from? And then if I have a flat mirror, okay, the rays look as if they're going to be the same distance behind the mirror as I am in front of the mirror. And that's all just by drawing your rays, because I'm not going to get any distortion associated with those rays with a flat surface. Now, when I start curving surfaces like the Funhouse mirror, we're going to see that we're going to start getting some distortion, and we're going to see some changes associated with it. But if I got a flat mirror, I'm going to just use my law of reflection and reflection to get there. So looking at our conventions, and usually what's going to happen is I'm going to use, when we get to lenses, I'm going to use 3 rays to define my image. In mirrors, I just need 2. And actually, even in my lenses, I only need 2. The third one is just going to give me a check. So when we're going to actually draw and use ray optics, I can actually draw exactly where my image is going to be. So we're going to use the convention for my object. We're going to use the little arrow. That's my object. Some books will use a candle at this point, but that's what we're going to use. There's our original height of the object. And we're going to take a ray, and we're going to draw a ray parallel to my surface here. Draw a ray parallel to my surface, and I'm going to take that ray and I'm going to hit the mirror. I'm going to extend it towards the back. Again, this is on the virtual side, because if I put a piece of paper here, I won't see the image. And I'll get it to bounce over to the back, and it bounces straight back, so that's going to tell me where my image is going to be, and that's going to have a height, which we're going to call H prime. We're going to have a height H prime. And then I can go through where this surface bisects my mirror, and I can come in and I'll get a bounce here, and then I get my reflection and it bounces that. And now I take that line and I extend it back out, and where these two intersect is going to give me the height of my object or my image. So I'm going to use these conventions. Now if I have a flat mirror, and this is what happens when I have a flat mirror, my triangle, this triangle is going to be the same as that triangle, and because of that, the H prime is going to be equal to H, and my Q is going to be equal to P. So the image is going to appear to be behind the mirror the same distance as the object is in front of the mirror. But it helps us start to identify where we're going to use our sign conventions and everything associated with it. We're going to talk about magnification And magnification is going to be defined as the image height divided by the object height. So in this case, my magnification is 1, because h prime is equal to h. My magnification is going to be 1. And my magnification is going to tell me whether or not I have an image that's bigger than the original object or an image that's smaller than the original object. And if the image is smaller than the original object, it's going to be something between 0 and 1. So 0.5 means my image is going to be half the size of my object. And if I have 1.5, my image is going to be 1.5 times the size of my object. So magnification is going to be related to the image height divided by the object height. And as we get into lenses and we get into other mirrors, we're going to learn that it might be negative, and the negative means I flipped my image over. So in this case, my image is going to appear upright, just like my object, and so I'm not going to worry about whether or not it flips over. Now, like what you guys did with your pinhole cameras, the image in your pinhole camera was upside down from the object. And so when you're doing your magnification, you're going to get a negative value. And so that's one of the things that we have to look at. So we're going to look at this. So I'm going to give you a second and I'm going to talk through it, and I'm going to go out on paper and we're going to write it here for a second. But this is in your book, and the object of this particular problem is how big does the mirror have to be in order to see the whole person in the mirror? Okay, how tall does my mirror have to be in order to see the whole person in my mirror? Now, there is a little bit of a misnomer here, because if my person is standing real close to the mirror, I'm not going to have enough room for the rays of light to get there. But theoretically, it would still work. Just that we all know if I'm right up on top of the mirror, I'm not going to see my feet. Okay? So this provides that I'm stepped back just a little bit behind the mirror, or in front of the mirror, in order to be able to see my feet. So we're going to switch, and I'm going to draw this out. Okay, so I got my stick person, because we all know my artisanal abilities are much like Dr. Seuss. So I got my stick person here. And I got my mirror. And we're looking for D. And here's where my eyes are, because I gotta have my eyes in here to look at it. So if I think about the ray from my feet, I'm gonna change my color. The ray from my feet, we want it to bounce right at the end of the mirror. And we want it to come to my eye. And if I use my law of reflection, this angle has to equal this angle. Now, my eyes aren't on the top of my head, as much as most mothers would think that's to be the case, or little kids think that's the case for their mothers. So I've got a little teeny tiny triangle that's hitting the top and hitting the eye here. It's also going to behave with the law of reflection. So what I end up with, and so I'm going to give myself some values here. So we're going to do A, B, C, then I'm going to do D, and then I've got F, G, and I'll do that one as E. Okay, so this is going to be a right triangle right here. So we know that AE is going to equal EC. That's one thing we know. We know that GC is going to equal GF. Okay, this and this, so BE D has got to equal EC plus CG. Okay? So far, the height of the person, so we're going to call this H. H is got to equal AE plus EC plus G or CG plus FG. Well, AE is equal to EC. So I got EC plus EC plus CG, and FG is equal to CG. I just wrote it backwards there. So now I've got 2EC plus 2CG. I'm going to factor out my 2EC plus CG, except that's equal to BD. And that's equal to D, which is what I'm looking for. So D is just 1/2 the height of my person. Just 1/2 the height of my person. I don't know if I've got my picture all the way up. That way we can see the whole picture. And I didn't do anything terribly complex. We just drew our rays. Just totally drew the rays. And your book actually steps through the same analysis. It's one of the examples in the book. But I always like the mirror problem because it's practical. Okay, totally practical. And remember, a lot of your magic trick illusions are a lot about how you're doing with mirrors. That's why they call it smoke and mirrors, right? Smoke and mirrors gives us the magic trick. I don't know if anybody watched it. Did anybody watch, what is it, Duff? It was Duff versus the Cake Boss. You had the Cake Boss and the Duff. And they did the magic trick. They did the actual illusion as part of one of the cakes. I'm getting blank stares. You guys don't watch Cake Boss? Well, then if you don't watch Cake Boss, I'll show you the illusion because it's pretty cool. Okay. So one of the tiers on the cake that he did, because they were making it for a party for Penn and Teller, all right? Well, so one of the things that they did is they took one of the layers and they cut the cake in half. So you've got this side of the cake was over here, and they put a mirror here. Now you could have done it 2 ways. They chose to do it a little differently. I would have done it as a checkerboard, but they chose to do it differently. They put a strip of icing here. And then they did 2 strips in a different color. So they did 2 strips. So they did this strip as black. And they did this strip as red. And then they did 2 strips of black. So of course this is not to scale, right? Not to scale. And 2 strips of black. And they did it with a ribbon so you could actually see the seam each place. So you could see that seam each place. So basically it kind of looked like this. So they had, in fact, they actually did do red and black. That was the colors they actually did. So inside on the mirror, you got the one black strip that mimicked this. So now everything was a 2-strip piece. And then you saw the 2 red strips. And then you saw the 2 black strips. So I have my little line through here, and then you saw the 2 black strips. So essentially, when you looked at the cake from here, it looked like you were just seeing straight through the cake. But if you turned the cake around, you saw the half of the cake, the disappearing cake. Total disappearing cake. The key is that because of everything that they had all together, you just got the illusion. Well, the cake's gone, and it really wasn't. So this is the origin of optical illusions. So you could actually do a disappearing cake. It's here on a disappearing cake. So I thought it was pretty cool. You can play with the optics to get your disappearing cake. All right. So another thing, before I go any further, I want to show you inside. I got to go back, see if it will take me back. It did. It took me back. We're going to talk about spherical aberration here. So this is why the Hubble telescope, this was another oops. This was an engineering oops. And so this is the Space Telescope, and it's got the history of the spherical aberration on the Hubble telescope. They essentially had to go up and fix the Hubble telescope, put glasses on it because of a spherical aberration. And we're about to define that spherical aberration. So I have put in there, because essentially what happened was, there's the galaxy with the way the Hubble telescope first went up into space, and that was after the aberration was corrected. And luckily it was an easy fix, but it was not all that great. And it was a really, really bad, a really big oops that we had associated with the Hubble telescope. Okay. From current side. So so when I'm doing a spherical mirror, or a mirror, and our mirrors are going to be radiated on arcs. This is called a concave mirror. So it's going to give me a bow in like this, so it's going to form like a cave. If I'm looking at this side of the mirror, we call that convex. Okay, so I'm going to get a concave side and a convex side of the mirror. And so we're looking at a concave side of the mirror, and we are going to draw our mirror as if it were part of a circle. That's the shape that we're going to get. And this gives us our center of curvature. So when we derive our mirror equations, we're going to start by looking at the center of curvature of the mirror. So if I put an object in, I'm going to have my object, and I can do my law of reflection, and it will be perpendicular right at that spot on the surface. It's going to be perpendicular right at that spot on the surface, and the light's going to bounce, and depending on my radius of curvature, I'm going to get a focal point. And we all have played with that a little bit. We've all played with a focus where all the light is going to come to one spot. Depending upon that radius of curvature, I'm going to get my light to come in. Now, if my mirror is perfect, absolutely perfect, everything comes to a single spot. If my mirror is not perfect, my rays are going to bounce, and it's going to do something like this. The other thing that's going to come into play is different colors will also do this. You'll get a chromatic aberration, where red will show up in one place and white will show up in another place, or yellows will show up in another place and greens will show up in another place. So you can get some dispersion as well, depending on how you've got your mirror set up. But the fact that my rays don't all come together at a nice crisp spot is what we refer to as a spherical aberration. My mirror isn't perfect. And when my mirror isn't perfect, things don't come together. And that's what happened with the Hubble telescope, is that we got that aberration that's there. So that's what it's meant by a spherical aberration. So when we do the ray optics for a mirror that has a curvature, this is how we're going to do it. I've got my object, okay, and it's going to work no matter whether I'm on the inside of the curvature or outside the curvature. The methodology is going to be the same, but it's easier to explain it when my object's outside of the radius of curvature. So if I do this, and I'm going to use what we call the principal axis, which is going to bisect my mirror. I'm going to put the center of curvature on my line. And it could say that the center of curvature is 3 inches, whatever my radius of curvature is, that's what I'm going to put on my line. And now I can draw 3 rays. I can draw that parallel ray. This picture doesn't show the parallel ray, but I can draw the parallel ray over to here, use my reflection, and draw it off, and it'll come down and it'll intersect in the same spot as these. So it only takes 2 rays to define my image, but that third ray is going to be a check. So I can use a ray that's parallel to my principal axis to come in and go down here. I will have from my tip of my image, object through the radius of curvature to the mirror, and that's the ray that's going to bounce back on itself. Then I've got the ray that goes from the tip to the principal axis and it bounces off. And where these intersect is going to be where the image is. Now, this is going to be a real image because I could put a piece of paper there and actually see the upside down aspect of my image. I could put, it'll be like shining it on a screen. I actually see it because the light rays really are there. Okay, the light rays really are in that spot. So that's going to be a real image. It's upside down. It's flipped over. And I can calculate the magnification because I can actually measure H prime and measure H and get the value. And in this case, the value is going to be less than 1, which means that my image is going to appear shorter than my object. My image is going to appear shorter than my object. So looking at some pictures, this shows where I've got parallel rays coming into a mirror and all the lights are intersecting in that point. My radius of curvature is going to be out here somewhere. And so this is my radius of curvature and this is my focal length. And it turns out for mirrors that R/2 is equal to the focal length. R/2 is equal to the focal length. And so we can actually rewrite our mirror equation. Now, if I'm doing it with a convex mirror, the idea is the same. Okay, the idea is the same, except now I have to go through my radius of curvature, which is behind the mirror. I'm still drawing this same line. It's behind the mirror. I still have this same line coming in, and I can go through the radius, the focus, to help me out to draw it. And this is going to be a virtual image because I'm not going to be able to put a piece of paper there and actually have it see. So it's my virtual image. So I can use those draws. So here's our sign convention, and that's where I'm going to cut it off today because we've got sparse folks. And we've actually got a little bit of time. That if I'm in front of the mirror, P and Q are going to be positive. P and Q are negative on the back side of the mirror. There's no light on the back side of the mirror. It's the virtual side of the mirror. And I'm going to have that negative sign is going to be there. And you'll end up with these sign conventions. So when you're making your cheat sheet for the final, you want to have your sign convention sheets there so that you keep those things straight. So you want to keep those sign conventions. So if I get a negative magnification, I get an inverted image, I get a negative value for magnification. That means my image is flipped. Positives are in front, negatives are in back, upright images are positive. And remember that the virtual image is the image that our eye sees as being there, but if I put a piece of paper right there, the light really isn't there at all. And we'll stop. And we'll see you guys on Wednesday.